The aim of this video will be to show the importance of the influence of magnetic fields of elementary particles of matter in building models of the structures of atoms and ions and their bonds with other atoms, ions and molecules on the example of halogen atoms and their ions. According to the ring theory, the structure of an atom's nucleus determines the properties of atoms, which defines the position and properties of electrons in relation to protons in the nucleus of an atom. The first representative of the halogen group is fluorine. According to the ring theory, the model of the structure of the fluorine nucleus consists of two globules whose axes are identical. One globule consists of 5 protons and neutrons. The other globule is made up of 4 protons and neutrons. They are bound to each other via a proton bridge and held together by the electromagnetic field force of both protons. The 10th neutron, which is located at 100% of the stable isotope of the fluorine atom, is located between the proton bridge protons. With its magnetic field, it strengthens the bond between the strongly electrostatically repulsive globules. One of the most important elements of the structure of the core model is the distribution and orientation of the magnetic moments of the proton rings. In one globule, the radial exterior magnetic moment vectors are directed from the globule, and in the second globule, the radial interior magnetic moment vectors are directed into the globule. This structure of the nucleus affects the orientation of the magnetic moments of the electrons, which are bound to the individual protons of the nucleus, but have an antiparallel direction to the magnetic moment vectors of their control protons. The second element in the halogen group is chlorine. The nucleus structure model of a chlorine atom consists of 4 globules bound to each other via proton bridges. The nucleus of the chlorine isotope is stable with 1 or 3 extra neutrons. Neutrons are located between the protons connecting the globules, and their magnetic field increases their cohesion. The chlorine atom nucleus model is terminated on one side by a globule with 5 protons whose magnetic moment vectors are directed radial exterior from the globule and the other by a globule with 4 protons whose magnetic moment vectors are directed radial interior into the globule. The third representative of the halogen group is bromine. The structure model of the bromine atom nucleus consists of 8 globules bound to each other via proton bridges. The nucleus of the isotope of bromine is stable with 9 or 11 extra neutrons. The nucleus model of the bromine atom is terminated on one side by a globule with 5 protons whose magnetic moment vectors are directed radial exterior from the globule, and the other by a globule with 4 protons whose magnetic moment vectors are directed radial interior into the globule. The last element in the halogen group is iodine. The model of the structure of the nucleus of an iodine atom consists of 10 globules bound to each other via proton bridges. The nucleus of the isotope of bromine is stable with 21 extra neutrons. The neutrons are located between the protons connecting the globules. The 2 neutrons between the globules form the alpha particle structure of the helium atom, which can connect the following globule to the same direction of the proton's magnetic moment vector. The model of the nucleus of the bromine atom is again terminated on the one hand by globules with 5 protons whose magnetic moment vectors are directed radial exterior from the globule and on the other hand by globules with 4 protons whose magnetic moment vectors are directed radial interior into the globule. It follows from the previous commentary that the models of halogen nuclei contain the same globule structures to which the bonding electrons bind. Based on this phenomenon, we can assume that halogen atoms will also have similar properties. To create models of the structures of halogen atoms, we have to start from the structures of models of their atomic nuclei. Each proton is bound with 1 electron with an antiparallel magnetic moment vector, resulting in the creation of a repulsive force between the proton and the electron. This force creates an equilibrium dynamic state against the electric force of attraction between the proton and the electron and keeps the electron in the atom in a stabilized position. Halogen atom models have their 5p-type bonding electrons divided between 4 electrons with parallel vectors of their magnetic moments and 1 electron with an antiparallel magnetic moment vector against the other 4. This division allows halogen atoms to form both a covalent bond and a non-covalent halogen bond with other atoms. To determine the size of the radius of the fluorine model atom, we have to determine the size of the electron radius 2p, the rotation time of the charge, and the electron current that is produced by the rotation of the electric charge around the circumference of the electron. The dynamic equilibrium distance of the electron 2p in the fluorine atom is given by the equilibrium between the electric force of attraction and the magnetic repulsive force on the axis between the ring of the proton nucleus and the ring of the electron. If we assume that the chemical bond is a force interaction, then we express the required electrostatic force in the axis by a relation derived from Coulomb's law, and the magnetic force in the axis is expressed by a relation derived from Biot-Savart's law. From these relations we can express the levitation distance. After substituting the known constants and calculated values, we get the equilibrium position of the forces, the levitation distance of the electron 2p5 from the proton of the fluorine atom, i.e. its atomic radius. An atomic radius is a quantity that is not precisely quantified physically and that is not constant under all circumstances. It is related to the concept of the atomic model. The most commonly reported value of the atomic radius of fluorine. If we quantify the magnitudes of electrostatic and magnetic energy at the dynamic equilibrium distance of the electron 2p in the fluorine atom, then the difference between their values represents the ionization, or binding energy of the electron of the 2p fluorine atom. Based on the above values of the fluorine atom model, we can also create a model of a single covalent homonuclear bond of a fluorine molecule. Fluorine atoms are bound to each other by bonding electrons in such a way that the magnetic torque vectors of their electrons are parallel. The equation of dynamic equilibrium forces to determine the equilibrium state of the bond distance will have a simplified form for its symmetry. The coefficient of 2.6 relation for the electrostatic repulsive force between the nuclei of fluorine atoms also takes into account the repulsive electrostatic force of the other electrons of the individual atoms. From the equations for the electric and magnetic force in the axis of the proton and electron rings, we will calculate the levitation distance. After adding the two proton-electron distances, we get the length of the bond. The length of the bond between atoms in the fluorine molecule corresponds to the experimentally determined length of the single bond of the fluorine molecule. Similar to the fluorine atom model, the chlorine atom has 4 bonding electrons with magnetic moment vectors pointing inwards to a globule with 5 protons and 1 bonding electron with a magnetic moment pointing outwards to a globule with 4 protons. This structure suggests similar properties of halogen atoms, only with different energetic electrons. Even in the bromine atom, 4 bonding electrons with magnetic moment vectors pointing inwards are attached to a globule with 5 protons and 1 bonding electron with magnetic moment pointing outwards to a globule with 4 protons. Example of a model of a bromine atom. To determine the radius size of the bromine atom model, we need to determine the size of the radius of the electron 4p, the rotation time of the charge, and the electron current. The dynamic equilibrium distance of the electron 4p in the bromine atom is given by the equilibrium between the electric force of attraction and the magnetic repulsive force on the axis between the ring of the proton nucleus and the ring of the electron. The electrostatic force in the axis is expressed by the relation derived from Coulomb's law, and the magnetic force in the axis is expressed by the relation derived from Biot-Savart's law. From these relations we can express the levitation distance. After substituting the known constants and calculated values, we get the equilibrium position of the forces, and thus the levitation distance of the electron 4p from the proton of the fluorine atom, i.e. its atomic radius. The value of the atomic radius of bromine reported in the literature ranges from 94 to 120 picometers. Example of the structure of the iodine atom model. According to the ring theory, 4 valence electrons of the same energy and the same type of p form a ring with a maximum value of negative electric potential for all halogen elements around them. In the center of this ring, the value of the electric potential is significantly lower. This phenomenon is called a sigma hole in the literature. Due to the anisotropic distribution of electrons, halogens are monovalent and their sigma hole is located in the covalent bond extension on the opposite side of the halogen atom. This sigma hole is characterized by size and extent. The magnitude is determined by the maximum of the electrostatic potential, which does not change for electrons, while the range is given by the spatial size dependent on the length of the atomic radius and rises to almost 3 times in the series F less than CL less than bridge less than I. Until recently, the existence of a sigma hole on halogen atoms was proven only indirectly through the determination of the crystal structure of organic molecules containing halogens, or was confirmed only indirectly by quantum calculations. In 2021, a team of Czech scientists conducted an experiment that managed to image a sigma hole on a bromine atom in real space using Kelvin probe force microscopy under ultra-high vacuum conditions with unprecedented spatial resolution of the electron charge distribution around the atom. The pictures accompanying the article about this experiment might mislead someone into thinking that there is a region with a positive electric potential on the surface of the bromine atom in the middle of the sigma hole. The experiment proves nothing of the sort. It is only a lower value of the negative electric potential than that of the surrounding electrons. The non-imaging of the sigma hole in the fluorine atom may be due to the insufficient resolution of the experimental method for a much smaller surface area and electron distance of the fluorine atom than for the bromine atom. How the sigma hole works according to the ring theory will be shown by the formation of the fluoride anion. A fluoride anion is formed when a fluorine atom accepts 1 electron. Fluorine is a very electronegative element, which means it has a strong tendency to attract electrons. However, this property cannot be explained in terms of electrostatic forces. In order to explain how a negatively charged electron shell can accept a negatively charged electron, we cannot do without a model of the structure of the fluorine atom itself, and without the use of the magnetic field of valence electrons. 4 bonding electrons belonging to the same globule have a parallel direction of magnetic moment vectors and therefore repel each other not only electrostatically but also magnetically. Their electrostatic potential is negative, forming an uneven ring. In its center, the electrostatic potential is the least negative and creates a so-called sigma hole. However, the electrostatic potential in the middle between the electrons is not positive, as some theoretical studies indicate. In the space between the electrons, a combined virtual magnetic field is created by merging their magnetic fields, which has an antiparallel direction of the magnetic moment vector to the magnetic moment vectors of the electrons that create this field. This virtual magnetic moment can be quantified. We can assume that the free electron gets to a distance where the repulsive electrostatic and attractive magnetic force are in equilibrium due to the environmental conditions. The condition is that the magnetic moments of the free electron and the virtual magnetic moment of the fluorine atom are parallel. After this point is overcome, the attractive force of the magnetic field begins to prevail, the free electron becomes bound, and moves to a stable position given by the plane of the 4 bonding electrons of the fluorine atom. In this way, according to the ring theory, a stable structure of the fluoride anion is formed. The electron thus bound will remain of the s-type, and its radius indicates the size of the ionization radius of the fluoride anion. After capturing a free electron, its radius decreases, and the size of the radius of the bound electron corresponds to approximately the fourth energy level of the electron of the hydrogen atom. The experimentally measured value for the ionic radius of the fluoride anion is 133 picometers. In a similar way, we can present the formation of the bromide anion. From the graphs for calculating electromagnetic forces, it is clear that the distance of capture of the free electron is much greater than that of the fluoride anion, and the magnetic force of attraction is also significantly stronger. This also results in a more stable bromide ion. The cause of this phenomenon is the greater internal energy of the electrons 4p, their stronger magnetic moment and their greater distance between them. The radius of the free electron corresponds to the size of the radius of the electron of the hydrogen atom at the fifth energy level and determines the size of the ionic radius of the bromide anion. The experimentally measured value is 196 picometers. It is common knowledge that halogen atoms can act as electron acceptors and interact with electron donor species. This type of non-covalent interaction is usually called a halogen bond. Halogen bonding is relatively strong and highly directional. The binding angle is always close to 180 degrees. The fact is that both the halogen atom and the halogen bond acceptor are usually negatively charged and should repel each other according to Coulomb's law. According to theoretical studies, this coupling is explained by the attractive electrostatic energy of a positively charged sigma hole with a negatively charged electron donor. Unfortunately, as mentioned earlier in the study, the positive electric charge was not confirmed for the sigma hole and the dispersion forces arise at nonpolar atoms, which halogen atoms are not. It is therefore necessary to look for an explanation of the halogen bond elsewhere. One of the possible theoretical solutions to this phenomenon is offered by the halogen bond model according to the ring theory using the interactions of magnetic fields of elementary particles. If the stabilized fluoride anion gets close to the axis of the benzene ring, it can interact attractively with the virtual composite magnetic field of the benzene molecule from the ring side, where the magnetic moment of benzene is parallel to the magnetic moment of the fluorine anion. Both the magnetic fields of benzene and fluoride anion are strong enough to keep the complex in dynamic equilibrium against the electrostatic repulsive force of electrons. According to the ring theory, the dynamic equilibrium distance of the benzene fluoride anion complex is determined by the equilibrium between the electrostatic repulsive force between the fluorine anion electron and the 3pi electrons of benzene, and the magnetic force of attraction between the magnetic moment of the benzene molecule and the magnetic moment of the fluoride anion, all in the benzene molecule axis. The aim of this paper, study, was to show, using models of halogen atoms and their ions, the importance of respecting the effect of magnetic fields for a deterministic approach to the structure of elementary particles of matter and their magnetic moment vectors when building models of the structures of atoms and ions and their bonds with other atoms, ions and molecules. Using these magnetic fields, their magnetic moment vectors and magnetic forces, we have shown the importance of the atomic nuclear structure model, which determines the structure of the electron shell and similar properties of halogen atoms. Based on the structure of the electron shell, it is possible to explain the phenomenon called sigma hole, and thanks to the existence of the magnetic field of electrons, it is also possible to present a model of the formation of halogen atom anions and a non-covalent halogen bond with other atoms and molecules. Magnetic fields and their qualitative and quantitative properties of all elementary particles are among the basic physical properties that are neglected by the model concept based on quantum mechanical foundations. Without the incorporation of the electromagnetic field into theoretical intra- and intermolecular analyses, no theories can be correct. Thank you for your attention and open mind. For more information, visit the www.ringtheory.eu website.